Well, thank you. As the other Brian has said, we're going to talk about fusion ignition today. And this is for the first time in human history, a team of scientists has gotten more energy out of a target than what they put in with the driver that was pushing it. And appropriate for this conference, just about everything that we do is founded on HPC and AI to achieve this worldwide first. So I'm Brian Spears. I have two jobs. One is as the deputy lead for modeling and simulation in our inertial confinement fusion program. That makes me a big fan of traditional high precision, high performance computing. And I'm also the director of our AI innovation incubator, which we use to partner with technology companies to build AI strategies for national security. And so that makes me a big fan of the AI piece of what we're doing. So this is a conference after my very own heart. As Brian said, for the first time in history, we produced more energy from the target than was present in the laser that drove it. So that happened on December 5th, shot named at NIF N22-1204. We created a plasma with a temperature of exceeding 100 million degrees that produced 3 megajoules of fusion energy out, and we put 2 megajoules of laser light in. The energy we got out is the same form of energy that powers the sun, stars, thermonuclear weapons, and that potentially could be an enduring source of clean energy. And for the first time, we can produce a tiny speck of material about the size of your hair that has the same composition and the same burning plasma dynamics that are in the center of a star. And we can actually manipulate that inside a laboratory setting. And as I said, HPC and AI are critical in designing all of this. So let's take the experimental leap and see if we can. First, let me mention that it's a gigantic collaboration. So the folks that worked on this, I get to talk about it for a team of about 1,000 here inside my laboratory. And our partners that have helped us make this work live literally all over the map of the United States and around the world. So Brian and I did an experiment. Let's see if we can make this work with a video here. Are you guys getting any sound?
No, unfortunately not.
Of course you're not. Let's try one other thing, and if we can't do the inspirational sound, then we'll.
I hear it.
All right.
Just need to go in full screen.
Let's do it. So this is to give you a feeling for the scale of the facility that we work in. Fusion ignition is a huge thing. That's a $4 billion laser facility that's been operational for about a decade. This is also an example of what happens when scientists get inspired and try and put a soaring soundtrack behind what they've done. But it does give you a feeling for what we're working on. This started back in the 60s and has evolved into something that is just a state-of-the-art feature of the engineering world. As I said, this is the same process that is driven in the sun. For those who don't know, fusion occurs when we cram two hydrogen nuclei together, and we do that using this enormous laser. Laser heats a target, which I'll go into a little more in detail later, and drives an implosion that creates those conditions that we find in our nuclear stockpile and in the sun. The main product that comes out of this is data, and we'll talk about the way that we compare both experimental data and simulation data. We've just stared inside the laser, and we can sort of back out and give you a feeling of the size of this facility. That's about 8 stories high, and you're looking over the Livermore Valley here in Livermore. So we'll give our PR team their due. No, not again. Once is quite enough. Are you guys able to hear me now?
Yes.
Perfect. Well, that was a good gamble, and maybe it paid off. So I will say I felt compelled to show that because I work at the National Ignition Facility. You can see our logo on the side of the building there. I started working here 18 years ago, and we didn't put that I in ignition until about 2 months ago. So it's quite exciting for the country, and I'll tell you a little bit more why. So NIF's a core part of ensuring a safe and reliable nuclear deterrent without returning to underground tests. So we no longer explode nuclear weapons underground, and we're able to test conditions that are relevant to keeping that deterrent alive using experiments like what we drive at NIF. It also allows us to probe really exotic states of material that can be found nowhere else on the planet except inside NIF. So it's the world's most energetic laser. It enables the study of extreme conditions, and across the bottom are some things to get you oriented about what we're talking about. There are 192 laser beams. I'll show you later that when you walk into our facility, you're actually inside the laser itself. It gets to the matter we heat to temperatures of about 100 million degrees. Units don't really matter once you get up to that temperature. The radiation itself has a temperature of about 1 million degrees. Densities are 100 grams per centimeter cube. So for reference, solid densities of the stuff around you are about 1. So we get things compressed to about 100 times solid density. Pressure is about 10 to 11 atmospheres. The pressure at the center of our very own star, the sun, is about 10 to the 8th atmospheres. So it's 100 times what you would experience at the center of the sun. And we diagnose the laser in the system with about 120 diagnostics, each one of which is about a $1 to $10 million experiment in and of itself. And that is the critical link between what happens in that facility and the HPC world. Because what we do on the HPC side is simulate these physical processes, run them all the way through simulated diagnostics, and then make direct comparisons of what we see from the actual experimental facility. Historically, there's been a gap between what we see in the facility and then the way we bring that back to our data center to do analysis. And what I'll tell you about at the end is ways that we're pushing those into real-time coordination with one another so that what we're seeing in the facility and what we're doing in the HPC world are becoming one. To give you a feeling of scale, it's huge. So you can put 3 football fields across the top. So since we're at a Stanford hosted conference, there's a Stanford football field for you. I myself am a Berkeley graduate, so apologies, but there's a Berkeley field, and then we've got Southern California represented as well. If we rip the roof off, inside here is our laser. It's 192 beams. The laser beams, let me get my cursor so that you can see that. These are the beam lines. This is a target chamber over here that we can, where we place our target and actually compute the fusion, produce the fusion. Those 192 laser beams, size of a football stadium, just wail on a tiny target. And this is actually one of those targets. They are made of high density carbon in its diamond form. And they are one of the smoothest, most highly polished things on the planet. So you can see that they're very reflective. We care about defects in these targets down to the size of a single bacterium. And so for the HPC world, this means that we have radiation hydrodynamics codes that allow us to predict and evolve from initial conditions that include those tiny little defects into the gross state of what we're going to see in our actual implosion experiments. So what do we simulate? We use multi-physics massively parallel codes to simulate the fusion process, and those codes have to get inertial confinement fusion in its integral correct, and that can be achieved in the physical world using high-powered lasers and in the digital world using high-powered computers. So the codes first start with a laser ray tracing that propagates to the inside of what we call a hohlraum. It's a gold oven that gets really hot and produces X-rays. So our high performance codes have to convert laser light into X-rays appropriately. Those X-rays fall on the capsule and they quite literally explode the outside of the capsule and crush the interior. So the momentum transport and the change of energy from radiation and falling into physical kinetic energy is a critical piece of what we're doing in our codes. Then there's the stagnation phase. At this point, the kinetic energy gets transferred into compression and a new set of physics packages kick in because thermonuclear burn begins and the fuel gets excessively hot. So radiation becomes an even more dominant term than it was before. And then finally, there's another place where the inertia of the shell is key. This is inertial confinement fusion. So that cooking mass of fuel will stay together as long as the inertia of the shell that's surrounding it can hold it in. Eventually, the central pressure from thermonuclear fusion gets so high that we disassemble that fuel. And it explodes and the lights go out because the interior gets cool. So this whole process has to be run in detail and in integral by high performance computing. To get that compression done, We can zoom out from the capsule and look at what actually happens in that hole rum that I alluded to. There are even more physics packages that are active to begin with. As the laser beams propagate into the hole rum, they interact with the material that is blowing off the capsule and the material that is blowing off the internal of this hole rum cooking oven. And there's really exciting plasma physics that goes on inside there. In fact, the energy can be transferred by interactions with the plasma between the laser beams. And getting that delicate balance right depends on the wavelength of the light. It depends on the plasma conditions. So we now couple all of those physical processes that I talked to you about before, the thermonuclear burn, the radiation transport, the momentum transport, gets coupled with laser plasma interactions in order to make sure that we actually distribute energy in our system the way that we need to. And so doing this detailed balance has really taken 60 years. It was conceived of in this seminal paper in 1972. It was actually classified for the decade before that. Somewhere in the 9 months after the invention of the laser, John Knuckles had an idea and said, hey, if we could make this thing big enough, we could put enough energy in to compress things to solid densities, and we could make fusion, which we could use to study the stockpile and to power the world. And 6 decades later, he is still coming into our laboratory at 93 years old. And he once told me that he wished I would hurry up and help the team get ignition because he was going to die someday, and he'd like it to be done before that. So for John, we got it done. One other thing that I'll show you is just how difficult the engineering is. This one relates a little less to HPC, but I'm gonna work through what's going on here just as soon as I can get my cursor back. So allow me to do some PowerPoint gymnastics, and we'll get that going for you. Maybe we will, maybe we won't. Here we go. Okay, we're going to skip that one because we've had enough videos for the day, and this one is being a little bit complicated. So having laid some of the groundwork for the way that inertial confinement fusion is driving this process, let me now dive into what HPC and AI are doing in these critical roles. We use HPC throughout, and then some AI comes in at the very end, and it really is in 3 phases. There is the design of our experiments, there is the understanding of exactly what we think we are trying to do, and then there's the detailed prediction of what we can expect to happen. These are all important for different reasons. For designing, we have to configure the laser and build the targets themselves. For understanding, we have to set specifications on those targets and make sure that they are highly polished and incredibly clean. And then for prediction, we have to set up those more than 120 diagnostics that I talked to you about at the beginning in order to be ready for the signals that they are going to see. When we got ignition on December 4th, well, it was December 4th titled shot. On December 5th, the implosion that we produced in the National Ignition Facility was the brightest thing you could see in the solar system from our planet. And we have to configure diagnostics based on whether we expect it to be dim or whether we expect it to be bright, and it can range over multiple orders of magnitude. So our predictions are actually quite important. All of this is founded on our central code capability, which is a far over 500,000 line code, depending on which packages we employ, and approaching 1 million, and has been developed over person years of programming expertise by the Hydra team. So Hydra is a full physics 3D radiation hydrodynamics code that we use across the national ICF program. It runs on every gigantic top 500 platform that we have across the National Security Administration and at multiple other DOE labs. We use it to model detailed ICF experiments. And it's distinguished by the fact that it runs a broad variety of physical processes. They are in outline, shown over here on the right. I won't go through all of the details, but it propagates the laser light, as I've shown you, takes care of ion beams that are created in target experiments and through implosion physics. Radiation is a heavy occupant radiation transport of our code, and uses about half of our cycles when we run on typical machines that we use. The atomic physics makes up the bulk of the rest that isn't radiation transfer, minus a piece for hydrodynamics and The main show, which is burn products, is actually computationally much smaller than getting the atomic conditions correct, transporting the radiation, and then doing the hydrodynamics to do that propagation. Another important point for those folks here, it's under constant development. So if you're excited about anything that we say today, Brian has mentioned that there are lots of students from Stanford and elsewhere around. I'm going to show you ways that you can come join us. And if you've got a software interest on the HPC side, we are open for business. So let's dive into those three pillars, the design, the understanding, and the prediction. Even our routine simulations are heavyweights by most standards. So this is the smallest simulation that we do for our design thinking. They're two-dimensional, meaning they are axisymmetric whole ROM simulations. Let me point to what you're looking at. The whole ROM is the gold case that gets heated by the laser beams that you see coming in here, false colored in blue and in red. The beams come in two cones, a so-called inner cone and an outer cone, and they heat up this gold plasma, they ionize it, and then drive a radiation wave that emits radiation back into this cavity. Inside is the capsule, which gets squished into this distorted shape. You can see a density profile of that capsule in here. One of these simulations typically runs on somewhere between 1 and 50 nodes, maybe a handful of nodes, and we run it for 12 to 48 hour runtimes. This is sort of our thinking loop in the ICF design process. So we use it to make a quote unquote ICF design. So the ICF design is really two fundamental things. It is the shape of a laser power pulse as a function of time, shown here. It has this specific shape because we turn the laser on very bright at the beginning, and that launches a shock into the capsule target. This is a pie diagram of the capsule. So if you take out a pie-shaped wedge of the spherical capsule that we implode, there's deuterium, tritium gas at the center. There's a cryogenic layer of DT ice, a perfect single crystal of deuterium and tritium that is about the thickness of, about half the thickness of your hair, contained inside a diamond capsule. And we have to specify exactly the ratios of these materials, their composition, and the way that they're built and polished. When we turn the laser on, we drive a shock wave into the shell, which deposits entropy and sets the compressibility of the shell. We do that another 2 times as the laser comes on, getting brighter. And then we crank it up to peak power, which is in most cases pushing 500 terawatts. Not the most powerful laser on the planet, quite powerful indeed, but it is the most energetic. So other more powerful lasers will give you something like a picosecond or a femtosecond pulse. We're going to have one of the brightest lasers in the world on for a whopping 8 to 10 nanoseconds, which doesn't sound like much if you're not a laser physicist, but when you're whaling on a millimeter cube target with that kind of energy, it actually makes a difference. We do precision shock timing adjustments with these codes, so we know whether or not we should turn the laser on 50 picoseconds earlier or 50 picoseconds later based on detailed experiments that we do. And then making the coupling back to HPC, we bring in the diagnostics that we've seen, couple those to our codes, and then benchmark those codes to make sure that we understand exactly how the changes in the laser brightness are propagating into hydrodynamic evolution inside our targets. This can be difficult because of the multi-physics. One of the most interesting things is something that I call the Ghostbusters effect. 2 sets of laser beams coming into this whole ROM interact with plasma waves generated inside the target, and energy can actually be transferred from one of the laser beams into the other beams, moving photons from one to the other. And so it's a bit like folks who know the original Ghostbusters movie when they have their proton packs and they say it's really dangerous to cross the streams. Well, in our physics, it actually is a little bit dangerous to cross the streams. Because we have a great physics team, we've learned how to detune the wavelength and separate the wavelengths of these things so that we can transfer just as much energy from one beam to the other as we want in order to keep the radiation environment spherical and make sure that the implosion isn't oblate or pancake shaped like this, but instead is spherical. And one of the things that we did to get fusion ignition on December 4th was to harness that power of separating the wavelengths between those two and make a highly spherical implosion at very high velocity for the first time. So coming back to HPC, these run on platforms which are, I have the luxury to say, mundane by in their computational backyard. Magma is a workhorse for us with a few tens of thousands of cores and a peak 5.3 petaflops, and it peaked at number 69 on the top 500. So that thinking your way through the process of how to adjust these targets based on experiment. We also use those to understand one slightly more detailed picture. We can extract the capsule from the center and forget about the laser plasma interactions that the Horam has already told us about, and now just crush the heck out of the DT fuel. And this gives us the ability to understand what happens as, say, we can make facility changes, like increase the laser energy, which we did on December 4th. We put just slightly more energy from 1.9 megajoules to 2.05 megajoules. Every 100 kilojoules of laser counts, and we're able to understand with capsule-only simulations where you can see bumps and bubbles and spikes that have grown from bumps and divots on the outside of the capsule that are perturbing our central hotspot. We now understand that those roughnesses can partially be overcome. The yield falls as you get rougher going to the right, yield being how many neutrons we make. If you can make the laser more energetic, then you can make yourself much more robust. And in fact, that happened for our ignition shot. I mentioned this 2D capsule simulation mainly for motivation because we usually don't stop there. And we go on to the full-on understanding phase. So understanding means that we're going to use 3D capsule simulations to try to probe the smallest length scales that we have in our computational arsenal today. So this will be something that runs on thousands of nodes simultaneously, now a single computation instead of a collection of them. Well over 1 billion zones of computational discretization in our meshes, and we'll sit on a flagship machine like, say, the Trinity machine, which peaked at the number 6 on the top 500. Sit on that machine for something like a month, sometimes 2 months. We do this to make these 3D pictures of incredible detail from all of the engineering features that touch this capsule. The capsule gets held in our Horam by being sandwiched between 2 pieces of something that is like saran wrap. It gets tented from the top and the bottom. You can see the imprint of where the saran wrap touches this capsule. If you look very closely, there's a ridge, a wave that's launched at the top and the bottom. Our saran wrap happens to be less than a few nanometers thick. And that's right, I did intentionally say nanometers. It's not that many atoms thick across the thing, and we still are able to resolve with the combination of direct simulation and reduced models, the effects of those very small features. You can also see a little jet poking in here. We have to fill our capsules somehow, and so we drill a small hole in them with a laser. We fill them with a tiny pipe that allows us to flow deuterium and tritium in, and then we fret endlessly over the fact that this essentially shoots our implosion in the head by injecting material into the DT fuel. And we've learned to minimize this through direct simulation at very high resolution, so that in experiments we can see that the fill tube injects a bright radiating blob that is going to cool off our central hotspot. And we can also partially recreate that in 3-dimensional simulation from very small scales, but capture the integral effects. So as I mentioned, this kind of effort takes us up to number 6 on the top 500, and now we're recruiting the kinds of horsepower that mean that the power measured going into it is in the tens of megawatts. So we're moving real material in the world, or at least real amounts of energy, in order to digitally predict how we move material in the actual National Ignition Facility. So that's a good example of capability computing, of showing how we recruit our entire machines to do something that is very fancy, massively decomposed, and coming up with a single answer after much effort. We also probe the limits going the opposite direction. We try to predict the outcome and quantify our uncertainties, emphasis on quantifying those uncertainties, by pushing the limits of capacity computing. We do that using something we call at Livermore cognitive simulation, which is a tool where we use AI to couple together what we do in the HPC world with what we do in the experimental world. We recruit hundreds to thousands of nodes, but now we're trying to perform upwards of 300,000. Occasionally we push toward the 500,000 simulations Each simulation is small and not super expensive. It'll run on a single node. It will probably run for 12 hours, but we'll make $250,000 to sometimes $500,000 of those things. And why do we do that? We do that because we're going to wrap a deep neural network with that is relatively complicated and modern, is multimodal, can handle images, time series, and scalars. We're going to wrap that surrogate, AI-based surrogate, around all of those simulations so that we can now probe our parameter and design space as quickly as we like using AI inference. Instead of taking 12 hours to run a particular point, we've already done the pre-compute. Now we can do inference in milliseconds. So that allows us to look at a selection of experiments labeled here in the multicolors. We look at the experimental data. So these are actual neutron images. If you had neutron-based vision and you could see images based on neutrons coming off things, this is what you would see when you look inside the National Ignition Facility. We can ingest those images and then do a Bayesian inversion with our AI wrappers and say, how much in our coded language, P2, which is the amount of mode 2 asymmetry, how pancake shaped or sausage shaped is the implosion as a function of time as it swings from being shaped like a pencil to being shaped like a pancake. We can infer, though we can't measure that directly, what the time history of that looks like on each of these shots, and then build up a statistical model for what we might see on the next experiment, constrained only by the experimental diagnostics that we see, with the caveat that we're viewing it through the lens of our HPC and AI wrapped model. That has allowed us to do things like predict what we expect to happen in diagnostics when we field an actual ignition attempt. So we made a tiny splash compared to ignition on August 8th in 2021. And that shot gave us a megajoule of yield. It was about 70% of what we put in with the laser. It did some very interesting things to the plasma physics. There's this capability for the fuel to be very compressed, measured by a quantity called the downscattered ratio, and to generate neutrons, which we measure from fusion yield. And it walks up this S curve. In August of the preceding year, we predicted that we would be somewhere in the middle of this S curve, but not up into the peak where we would like to be. For December 4th, 22, we predicted instead that given the changes that we'd made to the symmetry, understanding the way we were going to shape the capsule as a function of time, that we had essentially done this thing over here on the right. This is the marginal distribution of the yield, and we went from having a lump that was below the 2 megajoule line, which I'll draw on here, that was the ignition line, to a lump that was above it. So we were able to recruit our experimental data and our HPC data coupled together with AI to make an accurate prediction. For the first time, the National Ignition Facility went into an experiment with a better than half probability of igniting, and indeed that's what happens. To do these kinds of operations, we move into the brave new world of heterogeneous computing on supercompute platforms. So we recruit the Sierra machine, which peaked out at number 2 on the top 500 list. It's a gigantic machine, had 125 petaflops, and allows us to recruit both CPUs and GPUs for doing the high precision computing and also for doing the low precision flexible AI inference and training workloads. So we move through the whole suite of the high performance computing and AI simulation world. So that is the state of the art as we have practiced it for getting to fusion ignition. And as I advertised in the abstract, I want to take a look ahead at what we're doing in the future. So ignition provides us a fresh impetus for the exploration of inertial fusion as a path for clean energy. So IFE has been a grand challenge, which is, in the old fusion joke, is 30 years away and always will be. But with fusion ignition in December of last year, I no longer believe it's always going to be 30 years away. I think we'll see inertial fusion energy in my lifetime, and I certainly believe in the lifetime of my children. Realizing IFE, however, is going to require new advances in science and technology. There are an enormous number of public and private ventures now that are growing really rapidly to do this. And we're working together with those private partners to try to make a successful industry inside the United States for developing real commercial fusion power. But for this audience, you should recognize that IFE and getting there requires critical advances in HPC science. So let's take a look at some of the things that we need to do next. The way that I see the future from the place that I feel fortunate to sit is that it's an extremely exciting time in HPC for ICF, and we're doing three things: probing ICF capabilities, that is trying to recruit that workflow that I showed you in order to say, what can we expect from future experiments? We have to get better at understanding exactly what's going to come next. We need to accelerate extreme experiments. To make inertial fusion energy, you don't get to do these ignition experiments once in history or once a month or once an hour, but you have to do them something like 10 times per second. So there's a gap in getting HPC and AI to be real-time commodities that we can recruit at the edge, and we'll talk a little bit more about that. And then there's searching new digital frontiers. We're coming into the exascale computing era, and we need to understand how to recruit that extreme scale computing for next generation design and optimization. We've only really looked under the lamppost in the past, guided by human intuition. Now we can couple that insight with enormous machines to find out where the best designs located in these huge design spaces. So let me give you a quick look at that. Segueing from where we were before, we predict with uncertainty multiple observables for upcoming shots. So we can recruit those cognitive simulation techniques for statistical models. We've got another attempt coming up in February. These things do not always go the way that we hope that they will go. You can see that as noted by these large distributions. In blue is the expected outcome, but we were at a place where the probability of igniting another target has moved up to about 60%. So we can have a bad day. That's totally possible. We could come in down in the tail, but if things go as we hope, we're going to do this again. And we've gotten it so that the prediction using our HPC and AI resources does not take us the months that it used to, but we've recruited more effective workflows and faster computers, along with new AI techniques like transfer learning, to get us to these new designs in a matter of, I would say we're at sort of 8 to 12 days. So the future is not just doing what we've done before, but doing it faster back in the data center and making sure that we propagate uncertainties through these systems. Next, I mentioned we need to do experiments that are extreme physics, and we need to do them at extreme rates. So HPC and AI at the edge are changing how we couple computing and experimentation. For the NIF scale, I mentioned we've got 120 diagnostics staring at this event. We slowly offload that data from the facility. We bring it back into our data center, and over the time scale of a couple of weeks, we decide what happened. We have a lead time of about 6 months to design a target based on that. And sometime approaching 9 months, we can react to what we saw yesterday. So we have this large air traffic control pattern of shots that are lined up and new shots that are coming in to fill the pipeline. We have work at a high repetition rate laser at Colorado State, where the laser is capable of firing at 3 hertz. And we've taken a hydrodynamics model, wrapped it in an AI surrogate, and pushed that model out to the edge on a computer that runs directly adjacent to the experiment. And that little AI sentinel that's running there is doing 2 things. Sometimes it runs the best possible experiment that it can. It compares in real time high repetition rate data that comes off the facility, compares it with the inference of an AI model on millisecond or shorter timescales, and then makes a decision about the next experiment that should take place based on the discrepancy between those, so that we can actually navigate to a better performing experiment over a matter of hours rather than a matter of months or years. We also sometimes do the absolute worst experiment that we can possibly do, which sounds a little weird, but we go to a place where our predictive model is just as wrong as it can be, because that's the place where we are poorly founded on data. In a high repetition rate sense, we can now go sit in that valuable landscape and collect as much experimental data as we can in order to elevate that model, usually by first a quote unquote black box method using AI and transfer learning to make it better able to predict what's actually going to happen. And then we go back into our thinking space and try to understand why that actually was. So this coupling, by pushing compute out to the edge, is changing the way we across DOE are thinking about high performance computing. There's very much a vision that the laboratory of the future, a laboratory like ours, like the National Initiative Facility, which costs $3 billion, or something that is even a much smaller, almost university scale laboratory, should have something like a 10 petaflop computer sitting there next to it in order to do both high precision compute and low precision AI inference. So this is new, it's very exciting, it actually works, which is amazing, and it's also a foundation for the way that inertial fusion energy should work. Then finally, there's probing the new digital frontiers. So exascale computers are enabling the exploration of these frontiers in very complex design spaces. We have 2 projects running here at Lawrence Livermore National Laboratory, really in order to be ready for the receipt of the El Capitan supercomputer, which is being built and constructed. We had to upgrade to ingesting 85 megawatts of total power on our site in order to power our Livermore computing facility. Part of that is to be able to support the El Capitan machine, which is going to be something like a 2+ exaflop machine. The first thing that we're running on that is something we call Project IceCap. That's inertial confinement exploration on El Capitan. We're running the entire hierarchy of those simulations that I showed you, from a very low resolution symmetrized simulations that I can run on a fraction of a node, but I can run hundreds of millions of them, all the way up to those 2D low res, 2D high res, to the super resolution with full-on direct numerical simulation of turbulent mixing. We've developed a process to recruit all of these 2 exaflops that uses a machine learning steered workflow to decide when it's appropriate to probe the gross lay of the land with low resolution simulations, versus when it's a very high value piece of real estate and we should pop up and do a super resolution simulation in that area. And by doing so, we think we have both cut down the amount of cycles and wall clock time that we need to explore these spaces, and open up the dimensionality of the spaces that we can search. So we can get out of 4-dimensional and 5-dimensional boxes and start pushing into 10 and 20-dimensional spaces where we can really understand real world physics design and engineering effects. So that's a view of the future from where I sit. I want to reiterate that this is the accomplishment building on decades of work and dedication by an entire community, the HED community and the HPC community. Here's a picture of Team NIF. There are a lot of us, and we've worked exceptionally hard to do this. But I'll point out the bottom takeaway on this slide is that we need you to help us change the world. Most of us working here really do feel like we're going out there and changing the way that we can think about science and power our planet. And there's some opportunities for you to come. So Brian asked me to point those out, and I'll highlight that we have about 8,000 employees on our square mile here in the East Bay in Livermore. And each summer we bring in about 1,200 students to be engaged in summer research projects. So these go from early to mid-level undergraduates up to very advanced PhD students. We've got about 3,000 PhDs on site, and we bring in about 1,200 students, so you get a lot of attention. Our average age on campus goes down substantially when the 20-somethings come on site, and those of us who are no longer 20-something have the pleasure of interacting with their enthusiasm. And it's a really great time to come in and work on that. It spans computing, data science, physical sciences, experiments, theory. There are opportunities for people everywhere. If you're a little further along in your career, you can come do a postdoc program here with us at Lawrence Livermore. Our postdoc program, one, pays quite nicely compared to most postdoc programs that are out there. Two, it pays in a different way by giving you 20% of your time, 1 day a week, to do whatever it is that you want to do to build your professional career. You can learn a new subject, you can write papers based on your previous PhD, you can build your professional network, you can do whatever you want to do with that 20% time. And there's a strong culture of professional development. So those of us who are mentors are judged and graded in our career development on the way that we make postdocs grow and succeed. So it's a really nice environment to be in. And then finally, if you're even further along in your career and you just want to network with us or take a small break, we have real sabbatical programs, but also what we call mini sabbaticals. So we will hire and pay part of your salary for 1 to 3 months. You're hosted by a staff scientist. You can keep up some of your university duties if you're obligated or interested in doing those, but you can also come out and think outside the box and do something new. You can, if you want, spend a full year with us, but if that's a little bit too burdensome, you can come engage with us for 1 to 3 months. So come as a student, come as a postdoc, come as an established professional. We've got room for all. The last word will be ignition. After 18 years of working on it, it's very satisfying for me to get to end with that. So I will stop there and return it to Brian. Thank you.
Brian, excellent presentation. This is fantastic. And those last few slides, I'm sure to grab. I'm going to give that to Steve. He's going to post that all over Stanford, at least. That's really great for our student community. So really appreciate you bringing that to our attention. We do have a few questions here. I'm going to start with the easy ones.
Okay.
Are those underground nuclear blast craters next to the NIF?
Though they are in the image, they do not exist there. Those craters happen at the National Nuclear Security Site in Nevada, formerly known as the test site, which did underground nuclear tests from shortly after the Manhattan Project until 1992. But no longer do we do those. And so, fortunately, they are not next to the ignition facility.
I bet. And this next question here, I think it referred to either slide 22 or 23 that you were on when this question appeared. Is what is the reason for long lead times between shots?
The reason for long lead times is multifold. Really, it's bottlenecked by moving and preparing material in the actual real world. So to produce one of those beautifully polished capsules that I showed you takes between 1 and 3 months, depending on how it's growing. They're built by sputter deposition, and we control them to less than a micron, and they grow slowly over time. Those have to be laser drilled, assembled, and built into targets. And so it takes us in all about 6 months to say, I want a target to look like this, to see it actually exist in the real world with the tolerances that we want, fully sealed, not leaking, and ready to go in the facility. And so there's a material lead time of getting in the facility. And then there's a cadence that's set by the operational pace of the facility. When we're making lots of neutrons, as we did in December, there's a very short period where those neutrons have made things briefly radioactive and the target chamber is hot. So we protect our staff and they get very minimal exposure. Nobody gets to go in for a couple days. And so it takes us some time to get the data and to get things back. And then we think on a time scale that says, okay, I just saw that thing. We're doing an experiment this week. I will get to think about that, think about the shots that I have planned over the next 6 months, make some changes, wait a few months to get a new target, and then we can get into in the facility and make a new change.
Great. Let's see. I think you probably answered this next one, but I'll let you repeat it. As you look into your crystal ball, when will fusion become a household power source?
Yeah, well, I've learned not to predict fusion matters. I was hired to this laboratory in 2004, and we were going to have ignition 6 or 7 years later. It's 18 years since I was hired, so much for those predictions. I did say I think it'll be in my lifetime. I think it's more than a 5-year thing for sure. I think it's less than a 30-year thing, and we're working very hard. Our laboratory has a new program focused specifically on IFE, and those of us involved with it are working really hard to shorten that timeline. And back to the student opportunities, if it's interesting to you, this is the one place in the world where you can come do it with a straight face.
I have to tell you, Brian, when I first told my son about the initial ignition and what this means to the world, the look on his face was just, he was absolutely incredible. And he was like, Dad, I'm so happy right now. I don't know why, but I'm really happy. So I had to explain it a little bit more to him, but
that's fantastic.
It's definitely getting a lot of attention in all ages. Interesting question here. A few years ago, Lockheed had an announcement of a fusion reactor approach. Do you have any insight on that?
Not a lot. I was aware of what they were thinking. If it's the one that I'm thinking about, it was an alternative scheme that was mostly magnetic, but maybe a hybrid, and it was supposed to be small. what I recall from the time was that it was interesting, but I think if you're a subject matter expert, you could look at it and say there were some real challenges. So the hope is that those will be successful. One of the things that we're doing in our IFE collaboratory is building public-private partnerships to work with folks like Lockheed to help bring the expertise that we have from actually fielding these kinds of experiments and producing these kinds of reactions, to put them together with their innovation and the commercial spirit of trying to make that commercially viable as a power source. So I literally have a conversation on my calendar with Lockheed for next week, and we'll see if that comes up again. But we're trying to make there be a vibrant fusion community so that ideas like that can come into existence in the US. If they're great, they can thrive. If they're not, then they can go the way that they should, as weak ideas, and make room for the really good ones.
Fantastic. I think, as you said, to make this really happen, it takes sharing of information between public and private sectors.
That's right.
Let's see. Can you please talk a little bit about the characteristics of the 10 petaflop supercomputer next to the experiment? How many racks, what CPUs, GPUs, et cetera? And what compute capability do you expect you may need in the near future for a smaller supercomputer?
Well, I'm happy to think about it, but I would invite whoever asked the question to help think about it as well. It's really just a notion at this point. Nobody has designed that system. Everyone has recognized that there are experiments that have different needs that are putting some evolutionary pressure on a machine like that. I think it is clear that it wants to be heterogeneous, that there needs to be a compute center that is high precision for doing what we would call real numerical simulation of what's going on. And there wants to be something that is low precision, that is flexible and repetitive and can do things like AI training and inference at high speeds, and that can balance the communication between those things. Outside of just what does that computer look like, there's a real trend in trying to understand data motion. How do I get information streaming off of diagnostics if I'm collecting it at hertz? Some experiments like at SLAC are operating at kilohertz frequencies, and so the speeds and feeds are just not clear. I would say work at the edge in this space, it's not quite clear where the bottleneck is, whether it's in compute, whether it's in latency, whether it's in bandwidth limitations for moving data, and maybe it's in all of those. So I can't answer you I can't say what the right answer is, only that that's an important question that this community needs to answer.
Fantastic. What role did uncertainty estimation play in the prediction and transfer learning success for NIF?
So uncertainty quantification techniques are sprinkled throughout what we do. We have a need to be able to predict things that we've not seen before, from stewarding the stockpile all the way through to protecting staff and protecting instruments. So UQ techniques, including traditional statistical learning like Bayesian inference, stochastic collocation, polynomial chaos expansion ideas, are involved. Transfer learning allows us to take that statistical learning and move it to a new context. And the major role that uncertainty quantification plays in terms of changing the way the experiments goes forward is to give us fundamentally realistic windows of expectation so that we can set diagnostics. You have to, for example, set the gain on a diagnostic. If you set it too high and the experiment is brighter than you thought, you will blind the diagnostic and you don't get any information. Conversely, if you set the gain too low and you have a dim experiment, your diagnostic will be staring in the dark and you won't see anything either. So the uncertainty quantification helps us set reasonable limits on the way that we configure diagnostics. And then it gives us a way to evaluate designs as well. When we have a new design, we can ask whether or not this new design, exposed to the same kinds of variations as we have already inferred, actually narrows up the predictive ranges of what we think we're going to see in the future. If it does, that's a more robust design and a place that we'd like to operate. So it helps us think, and it also helps us operate.
So news reports leave off the power it takes to fire the lasers. How do you see that improving?
Yeah, so news reports do that, despite the fact that every press release that we put out calls it target gain. To give you a feel for the power balance, we take in 400 megajoules off the grid. The laser is about 0.5% efficient, so it turns that into 2 megajoules of light. We make 3 megajoules of energy out of that. So that is the energy balance. To to make that energy balance work so what we did with the experiment is show that it's possible to get more energy out than what you put into that target. So the physics of the target are viable. That target doesn't know anything about how much energy it costs you off the grid to get that light produced. So the next thing that you need is a more efficient laser. There are laser concepts right now that rather than being 0.5% efficient at this laboratory are 10 to 20% efficient. So there's a factor of 40 change in that energy balance that could happen today if we're able to drive that to scale. The second thing you have to do is eke out slightly more energy from the implosion than what you put in. So we put in 2 megajoules of light, we got out 3 megajoules of energy for a gain of 1.5. If you get that gain up to about 10, which is not very far away at all, given how nonlinear these things are, with a 20% efficient laser and a gain of about 10, you can have an energy cycle that is commercially viable. So there are some ifs there. Those lasers have to 3 months ago.
Excellent. I know we have some more questions come in, but we're kind of running out of time. I'll let see if Brian will hang on and send messages via text. But I'll just leave this one last question. Is this worthy of a Rote Nobel?
People have asked that. I am probably not in a position to weigh in, but I will say that if I go back up to, certainly not for me and not for folks on my team, but if I go back up to this seminal idea with these 4 folks on it, they made a call in the months after the laser was invented that this could be a transformational way to do science for the national security and to transform the way that we power the world. And it's been shown that that is definitely the case. So if someone wanted to award a Nobel Prize, these are the folks that they should be thinking about. I'll leave it to the Nobel Committee to decide whether or not that's worthy.
Of course. Brian Spears from Lawrence Livermore National Labs. Thank you, Brian. I appreciate this. This was fantastic.
Thank you so much. It was a pleasure, and I'll hang around and